Here's my second question of the day. So let me start the polling for this. And this will delve into what the lecture will be about today. So we want to know which of the following would have the strongest attractive forces. And so we have dry ice. I'm trying to get it toward the picture. We have dry ice, which is solid CO2. We have sucrose. Let me launch the polling. We have naphthalene, which is C10H8. We have snow, which is solid water. We have sodium chloride, which is the table salt that we use, or similar. It's not iodized, of course. And then we have liquid nitrogen. We want to know which one of these would have the strongest intermolecular forces, aka attractive forces. And this is going to be discussed in the lecture, but we just want to see what the foundation is of students about this. So again, A, or dry ice, which is solid CO2, sucrose, sugar, naphthalene, C10H8, commonly found in mothballs, snow, solid ice, sodium chloride, which you find in table salt, and of course liquid nitrogen and water. I didn't put water because a picture of water because everyone knows what water looks like. It's water. Again, these are not for a grade. I just want to know the background of what you know before we begin. Give about another 30 seconds or so for those final, everyone to make their final answer. Another 15 seconds. Another 10 seconds. I need 6 more people to answer. And time. So let me show you the results, and then we'll go through each one in detail to explain how we know which one of these would have the strongest attractive forces. So here's the results from the class. As you can see, a variety of mixed answers. 20% say dry ice, 14% say sucrose, 21% say naphthalene, 16% say sodium chloride, 12% say liquid N2, and 15% say water. So now let me go through each one of these, and then we'll see which one is the correct answer. All right. So now we'll look at dry ice. The way you can kind of think of these is to kind of first think about what occurs at room temperature. So if you think about CO2 at room temperature, what does it do? Well, it's going to go directly from a solid to a gas. It's going to sublime. And remember that in the previous lecture talking about phase changes, when something has very weak attractive forces, it's going to go directly from a solid to a gas, sublimation. And so at room temperature, CO2 exists. At normal pressures, of course, CO2 exists as a gas. So here are very weak intermolecular forces for dry ice, because again, it's going to go directly from a solid to a gas. Next we have, excuse me, next we have sucrose. So sucrose is sugar, so obviously at room temperature and normal pressure, sucrose is a solid. So we'll label it as a solid for right now. Naphthalene at room temperature and normal pressure, it's a solid. But there's something interesting about naphthalene as well, which we'll come and revisit in just a moment. Snow is a solid, but as we all know, snow at room temperature will go to a liquid. So snow melts at room temperature and normal pressure. It'll go from a solid to a liquid. So since it's going to be a liquid, snow has very weak intermolecular forces compared to the rest of the examples here. So far we know that dry ice is not going to have the strongest intermolecular forces, and snow is not as weather either, because at room temperature snow goes directly from a solid, snow melts into water. Then we have sodium chloride. Sodium chloride is a solid at room temperature. Liquid N2. If you've ever had the chance to mess with some liquid nitrogen, what you'll notice is that as soon as you pour it out of its container, it immediately vaporizes. So at room temperature, nitrogen is a gas, because the attractive forces are so weak that to be a liquid it has to be very cold temperature. When you pour it out at room temperature, it automatically vaporizes. So this is a gas. So again, this is going to be very weak intermolecular forces. And then the last one we had was water, H2O. And H2O is a liquid at room temp. So we've gotten rid of dry ice because, again, at room temperature, CO2 is a gas, has very weak attractive forces. We discussed snow because it goes from a solid to a liquid. For example, at room temp, you're going to melt the snow, not very strong. Liquid nitrogen, we discussed that, if you pour it out of the container, it automatically goes from a liquid to a gas. It vaporizes, so N2 wouldn't be the strongest attractive forces. Actually, liquid nitrogen would have the weakest attractive forces. So we've narrowed it down to 4. We have sodium chloride, sucrose, and naphthalene and water. Well, water is a liquid, and the other 3 are solids at room temperature, so we can go ahead and get rid of water. Now we have to discern between sodium chloride, sucrose, and naphthalene. Now naphthalene, what's interesting about it, which is commonly found in mothballs, is that naphthalene goes directly from a solid to a gas. And that's how it prevents moth from coming, as it gives off that odor from the naphthalene. So since naphthalene sublimes at room temperature, it would not be the strongest attractive forces. Next we have left is sucrose and sodium chloride. Now both of these are solids at room temperature. They won't sublime at room temperature. So we have to look at, say, which one of these would have the higher melting point, would indicate which one would have the stronger attractive forces. So now if we put some sugar in a pan on the stove, and we put some sodium chloride on a pan on the stove, and we heated them both up, what you would notice is that as you add heat to sucrose would melt and then decompose into carbon, where we get the caramelized sugar. Whereas sodium chloride, if you heated it up on a stove, it wouldn't do anything. Likewise, you'll see that sucrose is made up of all nonmetals, whereas sodium chloride is made up of a metal and a nonmetal. So sucrose is a covalent compound. Sodium chloride is an ionic compound. And the fact that sucrose decomposes it may melt first, but then it decomposes at a relatively low temperature, means that sodium chloride, which is a salt, would have the strongest attractive forces. Because sodium chloride's melting point is very high because it has that metal anion interaction. And so out of all of these, sodium chloride would be the strongest. Liquid nitrogen would be the weakest. So that was just an introduction into attractive forces. Now we talked about earlier in a previous lecture, we talked about intramolecular forces. These are forces within molecules or ionic entities or metals that hold the atoms together or the molecules together. So we're talking about within a molecule, you have covalent bonds. Within a formula unit of ionic compound, you have ionic bonds. Within metals, you have in a metal, you have anions that contain cations and delocalized electrons. So all of these intramolecular forces are within an entity that we're looking at. And as you can imagine, when you break an intramolecular force, you're destroying the substance. So for example, we use sugar in our practice problem. When you heat sugar up enough, you break the covalent bonds, causing it to form caramelized sugar. So when you break those covalent bonds, it's no longer sugar. It's now another compound. So whenever you break intramolecular forces, you're destroying whatever it is that substance is. And intramolecular forces are always going to be a lot higher than intermolecular forces. So intermolecular forces are within different, for example, between different molecules or different atoms, for example. Now with ionic compounds, they only have ionic forces. So that's why they're so strong, is because you have this cation-anion interaction, and to break that, it takes a lot of energy. Whereas for covalent bonds, they're a little bit weaker bond because now they're sharing electron pairs. So again, these are all intramolecular forces. When you break intramolecular forces, you're destroying that substance. Now with intermolecular forces, this is different. So intermolecular forces were weakening or breaking the attraction between an ion and a dipole or two dipoles in molecules as well. And so intermolecular forces can arise from a number of different things. It can be from partial charges with molecules that interact with ions, or partial charges on molecules that interact with other molecules. So again, these are forces that are holding molecules together, or molecules and ions together. As I said earlier, these are a lot weaker than intramolecular forces. So the strongest intermolecular force is what we refer to as ion-dipole interaction. And again, these are referred to as non-bonding interactions because it's not a physical bond between the two entities. It's an attraction, an electrostatic attraction between them. And so ion-dipole is the strongest type of intermolecular force listed here. And it involves an ion and a dipole, so usually a polar compound. So if you have a salt and a polar compound, or you have a metal and a non-metal, say for example, you dissolve sodium chloride in water, well, the positive charge of sodium interacts with the negative charge of water, which is the oxygen. And this is the dipole-dipole, or excuse me, the ion-dipole interaction. So again, the ion of your salt interacts with the negative or positive partial charge of your polar compound. So it has to be polar because polar compounds have permanent dipole-dipoles. So the positive end of your dipole would interact with the anion, the negative end would interact with the cation. And this is what happens when you add salt to water when you're cooking, is that it's supposed to, as we'll learn in the next chapter, it elevates the boiling point, raises the boiling point of water. So that's why when people add salt to water, it increases the boiling point of water due to now forming this ion-dipole interaction. So a stronger interaction requires more energy to break it. So again, ion-dipole is the strongest one. It involves a cation or anion interacting with a polar molecule. So it takes two things for it. So for example, dissolving sodium chloride in water is an ion-dipole interaction. Now we get to hydrogen bonding. We're going to talk more in depth about all these, but hydrogen bonding is a particular type of what we call a dipole-dipole interaction. So very specific elements can undergo hydrogen bonding. So we're going to have a hydrogen attached to a very electronegative element, such as nitrogen, oxygen, or fluorine, that interacts with a lone pair of electrons on a nitrogen, oxygen, or fluorine. So only these three elements can undergo hydrogen bonding. They're one of the three most electronegative elements on the periodic table. So again, a hydrogen that is attached to a nitrogen, oxygen, or fluorine interacts with a lone pair of electrons on a nitrogen, oxygen, or fluorine. Now, if you take higher levels of chemistry, they will elaborate on this definition. But for us, these are the three elements that undergo hydrogen bonding. Because again, when you have one of these three elements and a hydrogen, you have a very polar bond. And since you have a polar bond, you have a dipole. So the positive end is the hydrogen. The negative end is the nitrogen, oxygen, fluorine, and then it interacts with a lone pair on one of those three elements. And then again, this is an attraction between those two molecules. And hydrogen bonding is a very strong intermolecular force. So water undergoes hydrogen bonding. Some other examples that undergo hydrogen bonding are methanol, CH3OH, ethanol, ammonia. So all of these fit the requirements of a hydrogen bonding. So that's how the intermolecular forces occur in these three substances, is hydrogen bonding between the OHs on different molecules. So ion-dipole is the strongest, and then hydrogen bonding would be the second strongest. This is when we're comparing, as I like to say, apples to apples. There are some exceptions that we'll talk about later. Third, dipole-dipole. Now, dipole-dipole the distance between the molecules, it will tell you something about the attraction between the different molecules and the strength of the intermolecular forces. Here, the distance doesn't really represent much, but if you were to measure the distance between the hydrogen on one molecule and the oxygen on the other, the closer they are, the stronger the intermolecular force is. So again, the closer your hydrogen on one molecule and the oxygen on the other are to one another, the stronger the intermolecular force is. And that's where they use X-ray crystallography to determine what that distance is between the molecules. Or if you had an ion and a polar compound, the closer they are, the stronger the interaction is. So intermolecular bond distances, the shorter they are, the stronger the intermolecular interaction. So with dipole-dipole, all polar molecules have dipole but dipole. So if you have a polar molecule, it's going to have dipole-dipole interaction. Now, hydrogen bonding is a subset of dipole-dipole. It's just a very strong type of dipole-dipole interaction. But anytime you have a polar molecule, you're always going to have dipole-dipole interactions present. And they're pretty strong interactions. Next, we have ion-induced dipole. So an induced dipole is something that's a substance that has a dipole, but it's not a permanent dipole. It's only induced for a short amount of time, and then it changes. And so an ion-induced dipole means you have a cation or anion that interacts with something that has, as if we want to call it, a temporary dipole. So it keeps on changing. And these are very weak intermolecular interactions. Again, we have a nonpolar compound interacts with a ion. That's an ion-induced dipole. So anytime you see the word induced dipole or temporary dipole, those are the main interactions, as we'll see in nonpolar compounds. So next we have dipole-induced dipole. So the only difference between that and ion-induced dipole is now we have a polar compound such as HCl interacting with a nonpolar compound such as Cl. Again, since it's nonpolar, it has a induced dipole or temporary dipole, and HCl is polar, so it has dipole. So this is a dipole-induced dipole interaction. Now for ion-dipole, ion-induced dipole, and dipole-induced dipole, you have to have at least two substances. So for example, if we just had sodium chloride, we cannot have ion-dipole. But if we have sodium chloride and water, we have a ion-dipole interaction. Likewise, if we just had Fe2+, we can't have ion-induced dipole. We have to have a nonpolar entity such as O2 to have that interaction. So the ion dipole, ion-induced dipole, dipole-induced dipole have to have two different entities interacting with one another. For ion, you have to have either a cation or anion as one of the two substances. And then lastly, the weakest type of intermolecular forces is called dispersion forces or London forces. These are just what we call temporary or induced dipole interactions. So very weak dipoles that result from polarizing electron clouds, and we'll talk about polarizability later on in this lecture. So all nonpolar compounds have dispersion forces. So if it's nonpolar, that's the main intermolecular force, is dispersion. When you have polar compounds, the main intermolecular force is dipole-dipole. Now notice I say main because you can have other intermolecular forces present, but those are the main intermolecular forces. So here's just some examples to kind of illustrate. We talked about ion-dipole. So what's cool about that is your anion, such as sodium, will interact with the negative part of water, which is the oxygen. And so you have these oxygens that coordinate to the sodium. And then you see that the hydrogens are the positive part of the water molecule. So then they're going to interact with the anion. So you have this interaction between the anion and the positive part of the water. And this keeps on going in, 3 dimensions, this repetition. So the sodiums interact with the oxygens, the hydrogens interact with the chlorides, and it keeps on going. Now with hydrogen bonding, again, it can be within the same molecules as long as it has those certain requirements, or it can be between different hydrogen bonding molecules. So here we have methanol, which has an OH it can hydrogen bond with water, which has two OHs. And so you see that the negative on the oxygen is interacting with the positive on the hydrogen for the methanol. And so that's the attraction that forms the hydrogen bond. The dipole-dipole interaction is between polar molecules. So here, for example, we have methanol, which is polar, interacts with the dipole on chloroform, which is polar. And for chloroform, the hydrogen is the positive part, the chloride is the negative part. And so you see the negative of the methanol interacts with the positive part on the chloroform. And this is a dipole-dipole interaction. Notice it is not hydrogen bonding because the oxygen is not interacting with a hydrogen that's attached to an oxygen, nitrogen, fluorine. Ion-induced dipole, a good example of this is if you take sodium chloride and try to dissolve it in hexane, you form an ion-induced dipole. So the ion interacts with its either the positive or negative end of the induced dipole. So here, since we're dealing with chloride, it's going to interact with the positive end. And if this was sodium, then the negative end would interact with the positive sodium ion. Again, this is very weak, and as we all know, sodium chloride is very difficult to put in solution. Next, we have dipole-induced dipole. We have acetone, which is a polar molecule. Hexane is a nonpolar molecule. So it's like if you try to put acetone in hexane, this is the resulting interaction. Again, the positive end of the temporary dipole on hexane interacts with the negative end of acetone, forming that dipole-induced dipole. And then finally, dispersion forces occur when you have two nonpolar entities. So like, for example, octane and hexane are nonpolar. Again, any compound with just carbon and hydrogen atoms is always going to be nonpolar. So when we talk about non-bonding distances, we're referring to what's called the van der Waals radii. And so the van der Waals radii is different than the covalent radii. Van der Waals distance is the distance between two non-bonded atoms in adjacent molecules. So for example, if this is one molecule, this is the other, the van der Waals distance would be the distance from one atom in that molecule to another. And that's how we know if a non-bonding interaction is occurring is the distance between those two molecules less than the sum of the van der Waals distance. So if you measure the distance between two molecules and it's less than the sum of the van der Waals distances, the distance, then it's an interaction occurring. And again, van der Waals radii is a little bit different than covalent radii. And one thing to note is that van der Waals radius is always larger than the covalent radius. To give you a few ideas, for example, hydrogen is hydrogen bonding with a hydrogen on another molecule. If you measure the distance between those two atoms and it's less than 2.5, then you would say there's a hydrogen bond. If it's greater than 2.5, there's no hydrogen bond. So that's how we use van der Waals radius or van der Waals distance to determine if there's an interaction present or not. So for an interaction to be present, the measured distance has to be less than the van der Waals distance between the two atoms. And this is showing you the difference. So I was a little bit off. Hydrogen is 1.1 angstroms. This is in picometers, actually. So the unit here is picometer. But to get angstrom, it's just divide by 10. So hydrogen is 1.1, oxygen is 1.4, but again, the sum is still 1.5. So if we look here, so as long as your measured distance between the oxygen on one molecule and the hydrogen on another, then is less than 2.5, hydrogen bonding will occur. Likewise, if we look at nitrogen, nitrogen has a van der Waals radius of 1.5 angstroms. So for nitrogen hydrogen distance, it would be 2.6 angstroms. So again, this is how we know if there's a non-bonding interaction is the nitrogen and hydrogen distance less than 2.6. And the less it is than 2.6, the stronger the interaction. Again, if you want to learn more about this stuff, X-ray crystallography is where we measure these distances between molecules. So when we get to ion-dipole forces, the main combination of compounds that gives you ion-dipole forces is when we dissolve an ionic compound in a polar solvent. So again, for ion-dipole forces to be present, you need to have an ionic compound and a polar solvent. And the polar molecule will be attracted to the cations and anions based on which side of the polar molecule is positive and which side of the polar molecule is negative. So for example, as we said earlier with chloride and sodium, the chloride is attracted to the positive ends of the water molecule and the sodium is attracted to the negative ends. Likewise with lithium ion, it's attracted to the negative ends and it forms tetrahedral geometry with the water molecules. And in this case, we're using acetone here. So it doesn't have to be water per se, it has to be a polar solvent. That's the main thing. Now water works the best, but any polar solvent will work. Now with dipole-dipole forces, these are the main intermolecular forces in polar molecules. So if you see that a molecule is polar, it's going to have dipole-dipole forces. So the partial charge on one molecule interacts with the partial charge on another molecule. So again, the arrow is the negative end, the cross is the positive end. And so they arrange in a similar fashion because these are permanent dipoles. And when you add energy to a polar molecule that's a solid, what you're doing is you're weakening that interaction so it becomes a liquid, but you haven't broken the intermolecular interaction.